back, everyone. We are digging in with the ladder logic programming class, not without a foundation. We spoke at the beginning that it is necessary to understand relay logic before we do ladder logic. And the reason being is at some point there will be a design for electromechanical function of a system before it can be converted into a fully automated system. And so relay logic is really the primitive way of doing ladder logic. And that's the reason we're studying this concept of relay logic. In our previous lesson, lecture 4, we looked into a variety of different kinds of inputs and outputs. And we consider manually operated, automatically operated, and some output types devices. We are now on lesson number 5. That's right. Lesson number 5. And this is what we call electrical schematic conversion to relay logic. What are some of the common configurations before we dig into converting between relay and ladder? So we want to take a look to the various ways of converting. As a matter of fact, it's not 3. There's actually 4 basic configurations. All right. So actually, if you allow me, I can just do this, right? So that we just talk about basic configurations. There's going to be 4, and there's multiple ones that come out of these 4 basic configurations. The first one is series, and that's called AND in the logic world. The second one is parallel, and that's called OR in the logic world. The third one is series parallel, sometimes known as SP, and it's called the AND OR. And then the fourth one is the inverter. A lot of the electrical logic configurations are going to be based off of this concept of series and parallel. So that's the reason why it's important. Think of series as something that depends from something else. Think as parallel as something that can function with something else or without something else. Think about series parallel, the combination of those two. And the inverter is the concept that it's kind of difficult sometimes for people to grasp. So I'm going to show you a few graphics here to interpret how that works. Okay, give me a second here. I'm going to pull that out. So here we go again, and we have here the basic configurations for the schematic conversions of relay into ladder. And I think it's important that you understand this concept because this will take you places as far as understanding ladder logic programming. All right, so the first one is I got a couple of inputs. We label inputs A and B. X in this case is the output. And what this configuration in series says is that A and B have to be in series for X to work. In this case, if A is true and B is true, then X will be true. Otherwise, F or X will be false, right? So that will be our series configuration, right? I'm going to go back that in a little bit so that we can review. The next one is what we call parallel branching or the OR logic. This is saying, right? Remember that the relay logic is made out of rails, rungs, branches, and so on and so forth. We discussed that in our earlier lessons. You may want to review that if you didn't understand that too well. And in this case, we have if A or B is true, then X will be true. And that's what we call the parallel or the OR configuration. All right. The next one is the series parallel. And that's a combination of series and parallel, just as the name implies. Notice here that I have A and B in series, and that is in parallel with C, which is read as AND OR series parallel. And once again, here we have the conditions of A and B being true so that X is true, or simply C being true so that X is true. So we have to look for the path where the energy will circulate from left to right so that the output is either false or true. So that will be our series parallel configuration. And finally, we have one that is a little bit awkward and different to understand for some people. But the basic idea here is that the default status of an inverter In other words, as this one is closed, the system will be energized, and as this one becomes open, the system will be de-energized. And so, in other words, think of this as this. This is the normal status of the NAT, and when you act upon it or you energize this input, as energy comes on, the output will be off. In other words, the default status is that nothing's happening for it to have this output energized, right? So as long as nothing happening, this is on. But then when I act upon it, or I electrify it or energize it, then it will open up the circuit. That is the inverter. Now, I think it's probably proper to introduce here a few concepts. And the concept we want to introduce here is what we call the truth table. All right, let me see how our time is doing. Oops. Okay, so it is recording. We're good. And so you're gonna hear about the truth table for these configurations. And if we want to create a truth table, we can. I'll show you how we do that. I'm gonna bring my text back here, and let's see text. I'm gonna create a truth table here, right next to the thing. And how big is the text? Not too bad. So I can probably. So we're gonna call this a truth table, all right? And the truth table will have A, B, and X, right? A are the inputs, B input, and X the output. So let's consider this possibility. So A is the energized, B is the energized, X is also de-energized or false, right? Right? Next possibility, we're gonna energize input A. I'm gonna keep the energized input B, right? Output X still false, isn't it? Or de-energized. Next, I'm gonna de-energize input A, energize input B, and X continues to be de-energized. The only time when X will be true or energized will be when input 1 is energized and input 2 or B is energized. So at that time, X becomes true. And that's right there our first truth table. All right, I wish I could just copy this. I'm not sure that I can do this. I might, but it's better if I just do a new one here. So I'm going to create another truth table here. I'm going to call that truth table. Actually, you can abbreviate by just simply type in TT. And our inputs are still A and B, and output is still X. Let's look at the different conditions. Okay, when A is de-energized and B is de-energized, X still false. You agree with that? It will be. But when A is energized and B is de-energized, X becomes true, right? That is correct. Once again, A de-energized, B energized, and X will be true. And of course, anytime both of them are energized, X will be true. So that is our truth table, logic table for this parallel logic configuration. Let's do this one right here. It's gonna be our next TT, and now we have 3 inputs, right? Don't we? A, B, C, and of course X is our output. So we have a little more to worry, but not too bad. Let's start by what we know. All the energized, right? And when that happens, this will be false. What happens when, let's do this, all right? A is de-energized, B is de-energized, but C is energized. What happens? You're right. X becomes true, right? All right, let's see one more time. A is de-energized, B is energized, and C is still energized. What happens to X? It's going to be true, right? All right, here we go. Now we're going to have all 3 energized. And of course, X will be true. Now we're not done yet. There's more possibilities, right? So let's just say that we have a condition like this here. Will X be still true? No. If only B is energized, X will be false, right? And I'm doing this not in order. I should have done it in order, but that's okay. You just have to look at all the possible conditions. We haven't talked about bits and bytes yet. I might introduce that topic somewhere else. But here are the possibilities. The other possibility we don't have is when these two are energized and this one is de-energized. All right, so A and B is energized and C is de-energized. This will be true, correct? Are we missing anything? 1, 2, then we got 3. All right, let's look at another condition. A is energized, B is de-energized, and C is de-energized. What's the condition of X? False, right? All right, so we got 1, 2, 3, 4. I think we're missing one more. Let's look at the possibility when A is energized, B is de-energized, and C is energized. You guessed right. This is going to be true, right? And I think we got it. This should be it. This should be it. And again, I didn't do it organized, but this is the correct answer. You have to look at the different inputs and how they enable the output so you can do your math and the logic behind that. So in this case, we discover that there is 3 instances when the system will be off and 4 instances, well actually 5, when the system will be on. Notice that any time that C is energized, the system will be on. So C is energized here, system is true. C is energized here, system is true. Energized here, system is true, and so on and so forth. And the last truth table, it's a simple one, right? Not so, but anyways, we're going to call this truth table, right? This is for the NOT or the inverter. And we only have one input, A, and one input, X. We didn't label that, but this is what it is. So this is going to be a little tricky. So when the A input is de-energized or 0, you're not going to like this, but this is X will be true, right? In other words, there's no energy going into this contact for now. But as soon as I act upon it, then X will be false. And you just want to keep in mind the NOT instruction of the inverter inverts everything. So if it's closed, it will open when it's acted upon it. If it's open, it will be closed when acted upon it. And so anyhow, a lot of information, but we need to be able to understand this before we move forward to anything else. This is the basic configurations for relay logic schematic, and very powerful. If we understand this, it's going to come very handy when we come to the point. Oops, I didn't want that. I just wanted to draw a line like done before. There we go. To represent that. Okay, so we're all set. Basically what we said is there's at least 4 basic logic configurations for relay logic and ladder logic. And they are series, parallel, and inverter. And there is the truth table for that. We studied those, and you can go back and review and try to make sense out of this. If you have any questions, just let me know. But it should make sense to you, right? That the 0 means de-energized or false. The 1 means energized or true, right? I could also have written in place of F0 and in place of T1, right? 1 is energized, 0 is de-energized. 1 is true, 0 is false. Those are the conventions that we use for that. So anyhow, I think we're doing pretty good, and the video is getting too big. Once again, this is your instructor for ladder logic programming, Professor Rodriguez. I will see you in our next class session. Thank you.